This video, along with all course content, including laboratory and hands-on activities, were developed by Andrew S. Heinz, PhD, and are copyrighted 2016, 2018, and 2020. All rights reserved. The student's course handbook serves as a guide and as a resource to the student throughout the course. It contains the sample problems done during class, laboratory activities, and practice problems to develop knowledge outside of the classroom. It is available on Amazon. We're good to go. All right, can everybody see it okay-ish in the back? All right, this is awesome. So 23 people. So Shreya's not here, is that correct? No Benjamin and no Anthony. And is there anybody here who doesn't have a name tag, who didn't already talk to me? Aside from poor Ava over there. Eva or Ava? Eva. Okay. All right, so I am Dr. Andrew Heinz. So the appropriate ways to address me in the class are either Dr. Heinz or Andrew. I don't care what it is, but it's not Mr. Heinz, right? So, welcome to tonight. So what we're going to do tonight is obviously we're going to talk about why we're going to be here. I see a lot of faces from the intro info session, which is great. So we're going to talk about why we're here, what we're going to do, and then we're going to take a small break, come back, and then I actually want to walk you guys through kind of a basic engineering problem solving, because what I'm going to be telling you about tonight is why engineering's different, right? That's what you guys are all here for, right? Is learn about how to be engineers, right? What we're going to do in this class is we're going to talk about the basics of being an engineer. I'm not going to teach you how to be a chemical engineer or a mechanical engineer. That would be the most amazing class ever, right? What we're going to do instead is talk about what it's going to be like to be an engineer, and how we're going to get there in the schooling you guys are going to take. All right, so first off, what is an engineer? So Ryan, I'm going to pick on you because you're right in front. What's an engineer?
Someone who can solve problems.
Someone who can solve problems? That's pretty good. Does anybody have a better explanation than that? No? Okay, because that's the right answer. Simply put, engineers are problem solvers, right? Maybe he's cheating. Maybe he's seen one of my presentations before. I think maybe, but that's okay. It's a great answer, right? But we're not just problem solvers, right? How do we solve problems? There's people who solve problems all day long. Is everybody an engineer? Maybe, kind of. A lot of blank stares. Right, you're going to get called on a lot. It's going to happen this semester, so just get used to it. Right? So we have a solid understanding of physical, chemical, and mathematical laws, right? So we take physics, we take chemistry, and we take math. And one of the weird secrets of the world is, as you start to take physics, what do you realize physics is just? A whole bunch of math, right? Then you're taking chemistry, once you get down to it, you realize you're talking about atoms flying around, and you're looking at them like little balls, and what do we realize? Chemistry is really just physics. Yeah, and then what do we realize math is? It's a bunch of tools, right? Math is just a tool that we use, right? Math doesn't actually mean anything, right? What is 2? It's a number, right? But what does it mean, right? Right? What is pi?
Number sequence.
What's that? Yeah, it's a number sequence. But what does that number sequence tell us, right? It gets us the circle, right? It gets us the area of a circle, right? But does it actually mean anything? The answer is no, right? It's just a tool that we use to represent something in the real world, right? So engineers also design, develop, and test basically everything. The desks that you guys are sitting on are going to get picked on a lot in this course, right? Somebody designed that chair. How did somebody design that chair, Emma? What do you think?
Way to think why you need a chair in the first place.
That's a very good answer, actually. Why do you need a chair in the first place?
So you can sit on it.
So you can sit on it. Okay. No, that's good. So no, I like that. That's a good answer. So what does that mean? So that you can sit on it. What does the chair need to be able to do if you're sitting on it?
It needs to support a person or anything.
Okay, perfect. It's going to support the weight. So is it Aditi or Aditi? Aditi. So she said that it needs to support her. What does that mean?
It needs to support your weight when you're sitting on it.
Mm-hmm. And what happens if it fails to do that?
You'll fall down.
You'll fall down? The whole thing will fall apart?
Yeah.
Right? So, Eva, how are you going to accomplish designing the chair?
Making sure it's stable enough.
Stable, okay. So let's take a look at this chair, right? Or this desk, I should say. Why are these legs at an angle? You don't have to answer these questions. These are questions I'm going to ask that an engineer would start to think about, right? Why might the legs be at an angle versus straight up and down? Why might they be at an angle?
Because it'd be better for the legs to like fall outwards than rather inwards.
Okay. And why? And yes, so it would be better for it to fall outwards or push outwards? To push outwards. Why?
Because like when like it's pushing inwards, it kind of puts too much strain on it.
Yeah, that's a great answer. Okay, why?
If it pushes outwards, then if it were to fail, you kind of like slump down. But if it pushes inwards, then once it gets past a certain point, the whole thing could like fall over versus like the metal just bending and
Yeah, and actually in that case you might have a failure mechanism where the whole thing actually just collapses under itself, right? But no, that's a great answer. So we just talked about the design, so there's a design aspect of it. What materials are it made out of? Got some metal. What's this stuff? Some sort of manufactured plastic material, right? But why are we using these materials? Yeah, they're low in cost. They're not wood because they're probably, I would guess that they're lighter per ounce than wood so that you can stack them better. What also happens to wood over time, especially when you have kids in the classroom who have pencils who are bored? They carve in the desks, right? I'm not saying you can't carve in these, but they're a lot harder to do than a wood desk, right? So you get durability out of it, so schools might be after, right? So we're gonna move on, but this is the type of stuff that an engineer thinks about, right? A lot more goes into it than just design me a desk, right? Also, why might those back legs be narrower than the front legs? What did I like to do when I was in a desk when I was in high school? Did I like to lean back, rock back a little bit, right? So you need to account for some kid not falling on his head so your company doesn't get sued and you don't get out of business, right? That's just the way it goes. Okay? So that's what I'm saying, fundamentally down there at my red statement. Engineers look at the world differently than other people do, right? It's my hope that after taking this class, you guys won't look at a desk and be like, oh, that's a desk. You'll look at it and be like, all right, I see that the legs are angled and stuff like that, right? And maybe not that particular instance. In fact, that's probably something that you don't need to do on your daily basis. But I think you understand fundamentally what I'm saying, right? So what's interesting is historically, I'm not going to walk you through a history lesson here, but it's part of understanding where we come from and what we're doing. Historically, engineering was just about infrastructure, right? The engineers in ancient Rome were the guys that, or the guys, well, it was guys back then. Sorry, ladies, it was, right? But it was the guys back then that designed the columns. They were the ones that came up with the materials and the concrete and the cement that was used to make things, right? And this was really just, it wasn't because someone was like, hey, Kate, we need the Acropolis built tomorrow. And she was like, okay, no problem, right? It wasn't because of that. It was because they needed to figure out how to live. They needed to figure out how to survive, right? So fundamentally, the people who could figure that out were the people who did better and were moved into these type of positions, right? And I'm not even talking like the Roman aqueducts. I'm talking about the guy standing in the middle of the field who needs to grow crops and realizes that there's no water there, right? Somebody decided at some point how to get water into the middle of a field. That was an engineer, right? Agricultural engineering, civil engineering. That's really where engineering itself came from. Today, obviously, engineering opens up a lot of opportunities with technology, right? I mean, that's when you think of engineering, that's pretty much what you think of these days is computer engineering, making things, making computer chips, stuff like that, right? That's really what you think about. But we absolutely have people who fundamentally need to keep our sewer systems going, keep our roads going, who whatever crazy guy out in Washington County who decides to put traffic circles everywhere, right? Those are all engineers. Yes, sir. Oh, no. Okay. Gotcha. No problem. So we become even more and more and more necessary, right? It's one of those things you're like, all right, we've solved how to do all these things. Do we still need engineers? And the answer is yes. We actually need more and more engineers because we keep creating more problems that we need solved, right? That's just kind of the world that you guys are walking into. So not only do engineers actually understand the math and science that we were talking about. And you guys did a great job with the breakdown of the desk of why the desk would be like that, right? You guys are critical thinking and that's what I'm looking for. But what we have to do and what engineers have to do is come up with stuff that's not just taught in the classroom, right? An engineer doesn't, I should say a successful engineer, doesn't just simply say, well, I was taught this in the classroom so I know how to solve the problem. Because Connor, as an engineer, what are you doing?
Solve problems.
Thinking to solve problems, and you're thinking to solve problems that haven't even been created yet, right? If somebody knew how to solve the problem, they're not going to pay you $100,000 a year to solve it. They're going to look it up in a textbook, right? So that's the real challenge that we as engineers have, is we have to take the stuff that we do know and use that to somehow figure out the stuff that we don't know yet and come up with a solution to it. And the trick there, and what's going to burn you many times in your career, I promise you, is that your job is to come up with the best solution. That doesn't necessarily mean it's the perfect solution. What do I mean by that? Does anybody know what I mean by that? What would the best solution be? Why would the best solution maybe not be the perfect solution or the ideal solution? Why is that?
It might not be necessarily cost effective.
My man, he got it. All right. So what I like to say, or not what I like to say, what I like to state, Einstein actually said, scientists investigate that which already is, engineers create that which already or which has never been, right? So a scientist is a person who wants to go in and fundamentally understand why things are the way they are, and we need scientists because without them, we can't know how things work, right? But scientists want to go in and figure out how something works. We as engineers, we don't really care about all the details. We just want to know what we can do with that information because we want to build something with it, right? Both are absolutely needed, but our job isn't to fundamentally chase down and understand what's going on. We want to just get to the end point to accomplish our goal, right? And that makes it sound very haphazard, like we're just all in there and trying to drive to the end, but that's not what I'm trying to say. What I'm trying to say is we don't necessarily care about all the tiny little mechanisms of a chemical reaction that are going to lead us there, right? We know that if we put fuel into the car and we turn the ignition, that we're going to get to go, right? That's what we want to do, okay? So I basically just summarized it here, but we both, and by we both, I mean engineers and scientists, we both take the same classes, but our goals are very, very different, okay? So when I was talking about the perfect solution versus the right solution or the best solution, the problem is that we as engineers, we have to design under constraint. And design under constraint, what that means is that we have rules to follow. And Andrew hit it on the head. The biggest one most of us have to deal with is cost. But also, what's another huge factor that we have to deal with? It's up there. The biggest one is time. For me, it's time, right? I work in a manufacturing environment. What can't I create more of? Time. I can hire more people, in theory. I can pay more to get stuff accelerated. I can bring more materials in, but I can't ever create more time in the week, except for the leap year. You get one extra day on the leap year. But okay, so simply finding any solution to a given problem isn't sufficient. We need to find what the best one is. But there's rarely only one way to solve a problem. Our job is just to find that best one. So instead of just talking in circles about that, let's use a case study example, okay? So Jordan, you are a civil engineer there was just a huge, let's say, what was it, a couple years ago, in the Philippines, there was a tsunami, right? And it took out their infrastructure, I believe it was Philippines, it took out their infrastructure. But either way, let's say you're over there. They have no water. Disaster-stricken area, they have no water. Your job is to get people water before people start to die. You've got a couple days worth of supplies. What are you going to do? Where are you going to start?
I'm there and I have supplies?
Well, meaning you have like water supplies, but you need to get people water. How are you going to do that?
Probably try to make a filter.
Okay, good. What else are you going to do? Right, so we need to get sustainable water to our people. So you're going to make a filter?
And make a way to transport it.
Make a way to transport it, okay?
Store it.
How are you going to power this?
I could use a bike if I don't have any energy.
No, I mean, no, so you're taking the next step, and that's perfect, right? But the point here is, given the immediate need for clean water, are we going to build a top-of-the-line treatment plant? No, it's going to take us like 2 to 3 years. It's going to be a ton of money. We don't have time for that. By the time we get our plant, what happens? Everybody done died, right? We failed, okay? So what we're going to do is we're going to take whatever military helicopter assets they dropped off, we're going to get some tank in place, and we're going to get water. And then what are we going to do? We're going to add on that and improve the system. Then what are we going to do? We're going to add on that and improve the system. We're going to come up with the best solution given what we have. Obviously, the perfect solution would be to build a water treatment plant. I don't think anybody's going to argue with that, right? Top of the line, solar powered, It's perfect. Runs on its own, fully automated. It's incredible. But that's 3 years out, and otherwise you don't want everybody to die. Does that make sense? That's all I'm saying, right? You guys understand what I'm trying to make, point I'm trying to make? You with me, Elsa? All right. So, said, an engineer's primary job is to develop the optimal solution given each set of challenges. And like you said, a lot of times that's your boss told you that whatever product you were trying to develop has to sell at market for less than $2. So you got to figure that out. So engineering is a profession. I will tell you, so I know your dad's an engineer. Who else in here has parents who are an engineer or in some profession of the sort? Yeah, a lot of you? Yeah, it tends to be in the Intel area we have that, which makes sense. So I work a ton. I get very frustrated at my job. I know your dad works a ton. Sometimes I'm assuming he gets frustrated at his job, right? Why do we keep going to work every day other than it's our job? But why not leave that job? We're highly employable. Why do we keep going back?
Because it's satisfying when you solve the problem.
Satisfying when you solve the problem. That's the correct answer, right? So as a group, despite the fact that engineering is very hard, as a group, engineers actually across the board generally report a higher degree of job satisfaction. And why? The answer is because to the engineer, the challenge itself is actually a reward, just like Kate said. Okay? So we get great satisfaction from solving complex problems until that problem's yanked away from you at the last minute because your boss is cutting costs, right? But that does happen. So for me also, I like to be able to go to Best Buy and know that something I made is in the laptops there, right? A lot of people get a lot of enjoyment, for a lot of engineers get enjoyment from seeing their product go to market, right? Not just because that's what's actually making you the money and validating you, but also because you actually made something that somebody's using, right? Some you guys all have iPhones, right? iPhones out there somewhere. Maybe some people have some Androids, right? Somebody designed that product. Actually, a lot of people designed that product, right? But they see somebody using that, that should make them feel pretty good, right? They were involved in that product. That's pretty cool, okay? So, and then the bigger thing is that engineers can make a difference, right? We use the example about the water thing, right? There are entire organizations out there of engineers that go and do that, right? The Navy has the Seabees. They fundamentally go in and set up infrastructure. There are disaster response nonprofits across the globe that do that, right? You can go in and you can actually make a huge difference. Even on the small stuff, right? You don't have to go in and save dying people, but you can come up with a new solar panel, a more efficient solar panel, whatever it may be that helps get us out of the hole that we're in. And then, hey, there's no shame if this motivates you, it motivates me, financially rewarding, right? You tend to make a lot more, well, not a lot of money, right? We're not like super billionaires here. But of the 10 highest paid undergrad majors, 6 of them are in some branch of engineering. So if we look at this plot, or not plot, chart, engineering, and this was 2017 numbers, so they're a little stale, but it's pretty much the same. So engineering is roughly 66.5. If you graduate, and this is graduating with a bachelor's degree, okay? So a new graduate coming out of school with a bachelor's degree, on average, makes 66.5, which is just above computer science, and a lot of people bundle those together, right? Engineering, computer science is at a lot of schools the same, right? But you can see that those two are very close. Math and science is below, business at 56, and then you just keep going down the chart, right? But engineering, you can make a lot of money. I mean, that is a support a family wage with a bachelor degree on a 4-year school, and that's pretty awesome, right? Now you got to get there. It's going to take a lot of work to do it. You can totally do it. All right, so of the highest paid engineering majors, just because a lot of people ask this, I want to run through this quick. So this is, again, as of 2017. Computer engineering has popped to the top. That is within the last couple years. When I first made this chart, started teaching this class, it was not at the top, but as you can imagine, things move around. Petroleum engineering still way at the top. That's because there's not a lot of schools that do that anymore, and a lot of people don't want to go into oil and gas anymore, so that one has actually jumped up quite a bit just because it's a little more in demand. Electrical electronics at 72, but you know, look at this, right? Computer engineering, you can start, that's your average starting salary, which means that some people are starting above that, others are starting below. $76,000 is a lot of money for a bachelor's degree, right? So, I mean, again, this is bachelor's degree candidates who finished school in 2017. Next problem, right? So this is stuff that you should be thinking about when you're going to school, right? I'm going to go pay, let's say, $200,000 to go get a college education. how long is it going to take me to make up that $200,000, right? If you get a degree in basket weaving, it's probably going to be infinite, right? But you want to figure out how long I mean, it is. That's what you guys need to be thinking, right? How long is it going to take me to recoup that, right? What am I going to do with that? And then furthermore, you need to think about how employable you're going to be, right? It doesn't matter if all the computer engineers are making $76,000 a year if there's only 2 of them, right? Because then you're probably not going to be able to get hired, right? Engineering continues to grow. Engineers are constantly in demand. And it's not just because old engineers are retiring, right? That's what you don't want to be in. You don't want to be in an industry where your dad has to stop working for you to get a job, right? That's not a good sustainable model. Engineering consistently grows, and in fact has been forecasted to grow approximately 11% over the next 10 years. Now, that doesn't mean that all engineering fields are going to grow, right? As you guys can imagine, oil and gas exploration is probably going to stay relatively steady. Oil and gas production probably grows a little bit. You could pick, mining engineering and stuff like that. Probably stays relatively stable, although if we decide to go after rare earth metals in the US, that'll actually probably change. And actually, that's a huge field. If we could figure out how to do that safely in the US, we wouldn't have to go to China and stuff, and China and Pakistan for our rare earth metals. That would be pretty nice. But the point is, with all of this growth, especially in tech field, right? It seems like every day there's a new, we are still we are trying to cost cut, but we are still hiring. Well, I mean, every company's trying to cost cut all the time, right? We're trying to cost cut, and we are still actively hiring engineers. Right? We're always looking for engineers, always looking for new talent. So again, 11% over the next 10 years. And the cool thing is, and this doesn't mean every job, again, not every job is safe ever. But even in times of economic decline, which you guys are, 14, 15, 16, most of you guys, right? So you guys were a long time ago. It was 11 years ago when the market crashed, so you guys haven't really had to deal with it. But even times of economic decline, our last depression, well, not really depression, but the last hard times we had, engineers still did relatively okay. It doesn't mean engineers didn't get laid off across the country, but the number of engineers who got laid, or the percentage of engineers who got laid off versus other fields, especially financial, was significantly lower, right? So, engineering disciplines, these are not all of them. But at some point I get tired of drawing logos, right? There are so many different fields of engineering, but fundamentally, they all boil down really to just these core stuff that we're going to be talking about for the next semester, right? What do you think those core learning values may be, right? So I've got I have actually multiple aerospace people who see hands who was interested in aerospace. Yeah, so I had a couple aerospace guys, more than normal. How about my biomedical, who wants to go cure cancer? A couple of you guys, all right? The rest of you don't want to cure cancer? Man, that's awful. It's a joke, all right. So civil, chemical. Just, what do you want? Civil, nice. All right. Anyway, so we keep going through it. So so Kate and Elsa, Kate wants to go be a BME, cure cancer, and she wants to go build bridges. What do they have in common? Not much, it sounds like, right? But do you know that they're going to be sitting next to each other in class for the first 2 years of their college education? Right? We're all learning, all engineers, we're all going to learn the same fundamentals. And that's what we're going to be covering in this class. What do you think those might be? Carson, what do you think one of them might be? Problem solving? Well, yeah, that's a given. That's a given. You don't get credit for that one. No, it's a good answer. Kate, what do you think?
What they have in common?
Yep.
Well, I feel like a lot of the foundation is the same, like a lot of the skills that they'll be using.
Mm-hmm. Like, what are those skills?
Well, I don't know, you have to understand, basic calculus to...
Yeah, that's a good answer. Yep. Chemistry, maybe? Circuits? Physics? Right? Just the fundamentals, right? And we're not going to be doing necessarily pure physics, but we're going to be doing what we call applied physics here. Now, that's not entirely true, because applied physics, who watches Big Bang Theory? That's actually what those guys do, is applied physics, right? When I say applied physics, we're going to be applying physics to actually solve problems and make it relevant to us in what we do. All right, so we're closing in on the end of this part. So I just do have a couple class rules that we need to talk about. First one, this is the number one most important one, is the buddy rule. All right, so from this moment forward, no one is allowed to be alone in this room with me without a buddy, right? If it's just me in the room, then you're more than welcome to be here as long as you have somebody with you. That rule is more for my protection than yours. And if you don't understand that, then please ask your parents, right? Okay. 2, we already talked about how to address me, right? It's Dr. Heinz or Andrew. Either way is good. Number 3, you own your learning. What do you think I mean by that? What do you think I mean by that, Rana?
I guess like I can't work it out, but like try to like stay on task and like if you goof off, then like
Yeah, that's fair. What I more mean by you own your learning is if Emma is sitting there, and I'm not picking on you because you're playing with your hair, that's not it, but if Emma's sitting there and she has no idea what the heck I'm talking about, right? This is a class that you guys choose to come to of your own decision, right? You guys, like, maybe your parents are like, you know, poking with a fork out the door or something. Like, I guess that could happen. But you guys choose to come here and you choose to be here and you choose to pay attention or not. If you don't understand what I'm talking about, you're wasting your time, right? Stop me. Ask me to explain it, right? That's what I'm here for, right? And furthermore, like she said, right, if we're doing a lab activity, you guys are going to go off and you guys are going to do the lab activity, and I'm going to be walking around and like just making sure people aren't setting themselves on fire, right? Your job is to get out of it what you want to get out of it and learn what you want, okay? We very much treat this as a college prep class, right? And what I mean is, like, when you guys go to school and you take your chemistry lab, you're going to have one TA in the room. There's going to be like 40 people, and you're going to be playing with a Bunsen burner. And like, aside from setting yourself on fire, your TA does not care because they're probably doing their homework, right? You're going to go through the lab notebook and you're going to take out of it what you're going to take out of it, right? It's the same type of idea. Okay, and it goes for the classwork too. I'm not going to assign you guys, well, I am going to assign you homework, but I'm not going to come in and check your homework. What I'm going to do at the end of classes, in your books, I have some recommended practice problems. I'll say, hey, based on what we talked about today, you go do these. If Andrew does it, great. If Carson doesn't do it, that's great too, right? You guys have other priorities that is not this class, right? Depending on what your tests are going to be. And doing a practice problem versus getting a B on your math test is probably not good for your answer either, right? You guys, or for your lives either, right? You guys own your learning. You guys own your priorities. You guys are responsible students. That's why you're here and you know what to do, okay? That's all I mean. Number 4 kind of goes in with that, right? Be open and communicate, right? If you don't understand what I'm right, if Ryan's like, hey, you put the wrong name on my card, say it. Don't just be Matthew for the semester, right? I appreciate that, right? Let me know what's going on and let me know if something's not working. We also have a flexible schedule, right? So I'll show the class schedule in a little bit, but that's flexible. I've had years in the past where we've changed the schedule because people just didn't want to know about one of the subjects. And we actually have a subject at the end that's open up, or we have a lecture topic at the end that's open, and we'll let the class vote on what they want to hear about, right? Last year we did solutions to cancer. We've done other stuff in the past as well. Okay? And then number 5, so again, as of this moment, we cannot have any food in the classroom, right? That's smart to begin with from a lab standpoint, right? It's bad practice to be doing lab activities in general with any food in the classroom. There are a couple exceptions. We're going to do one lab where I bring in candy. Obviously, then there can be food in the room, right? That's okay. But I need to have no food in the room at all. I have no problem with water and stuff like that, right? But please, no munchable food in the room. The other reason is because, again, we're borrowing this classroom because the teacher's very nice and lets us use it. If we trash the classroom, he's not going to let us use it, right? So, all right. Class starts promptly at 6:30, except for today, which was my fault, right? So what we're going to do for the first 15 minutes or so is we're going to go through a presentation topic. Most of the time that will be a different type of engineering, right? Usually we start with aerospace and just kind of go through, but it'll try to relate what we're talking about there, right? Other times we'll have guest speakers come in. I already have 3 lined up for the semester. I'm trying to get a couple more. It's been a hard year, actually, because just most of the people who I know are having kids and stuff, right? So it takes time. After that, we'll go into our lecture. The target is that the lecture will be done by 7:40, and then we'll take a quick break, and we'll come back and do our lab activity. Sometimes the lectures go long, sometimes they go a little short, but that will be the goal. And then there will be some weeks that we won't have a lab unit. That'll be weeks where we either have a longer lecture, we have a double lecture, or where we have a speaker come in or something like that. Because one of the speakers who comes in, if he comes in this year, he works for a company called Brain Lab, and he actually lets us play with his equipment, and that's way more fun than listening to me talk, I promise you. Okay? So, brings us to this. So, I did not hand these out and will not be handing these out this week, The reason is Amazon screwed us. They only sent us 7 of the 23. So this is the handbook for this year. What it has is sample problems in the back, but in the front it has the problems that we'll be going through in class, right? There's actually at some point in class we'll be going through something. I'll be like, stop, turn to page 25, and then we'll do this little sample problem, just kind of go through more like a learning activity as we go. And then in the middle, that's a bad page, that looks super technical. There we go, there's some drawings. In the middle, we have our lab activities. Okay, and usually I let you guys go through these, but again, I didn't. We only got the 7 from Amazon. They will be here Thursday, so they will be here next week. Okay, and then I'll hand out pencils next week as well. Those books are meant to, like, they're workbooks. They're meant to be written in, so that's the point of that. So you guys who brought notebooks, highly encourage you to continue bringing them, but that doesn't mean you can't write in that book. That book will be yours. It's yours to keep and write in and take notes. All right. So, and then I also have a shameless plug. So most of the stuff from this course comes from the textbook that I wrote, which is their Introduction to Basic Concepts Engineering for Advanced High School Students, or for Adept High School Students. It is not necessary at all to have the textbook for class. It is I think it's $100 on Amazon, so it's not necessary at all. Most of the stuff in this class does come from that book because obviously it's my stuff and I like to reuse images because then it takes less time, right? But again, it is not necessary to have it, but I'm just throwing it out there if you want supplemental stuff. So again, it is, I think, an excellent resource, but I'm biased because I wrote it. So, course outline. Right now we're on week 1, February 4th. Do note that it looks unlikely like we're going to have any weather events this year. But if we do have a weather event, this class follows Beaverton School District cancellation policy, right? So if after-school activities are canceled, this is canceled. If there's no school that day, this is canceled. Sometimes I think they have late arrival and still have after-school activities. I think that's a thing. If that's the case, then we'll still meet, right? But if this gets blown out of the water because of a weather event, we'll just push everything 1 week and we'll figure out where to take it out later, right? It's not a big deal. We've dealt with it many years in the past. Hopefully it won't happen this year though. March 25th will be spring break, no class that week. Basically, if the school is closed, we're closed, right? Anyway, so we will go through, next week is units and conversions. That's the one thing that absolutely everybody needs to know. Hopefully you guys know that already and it'll be quick. Then we're gonna go through engineering mechanics, circuits, power and energy, thermo, and then reliability. Reliability is the one I always like to do before spring break because it's nice, easy, calm. It's pretty fundamental and everybody gets it. After that, we'll do intro to fluid mechanics. This is the one where we always make a mess in the room because we spill water everywhere. Engineering statistics and process control. That's the candy lab. All right, we're going to be using Skittles this year. Then we have material energy balances. Manufacturing and industrial. That one's fun. We bring in my wife, Amy. We come in and last year we built Lego cars, right, on the production line to get an idea of how it worked. We then have materials. Materials is fun because we get to break stuff. We then have computer engineering and bioengineering, and then May 19th is the week that we have that May 12th will be the week that we have the floating lecture determined by your guys' vote or requests. Then at the end of the year, we will have a design competition. I think I'm probably going to do the same one we've done for the last 2 years because it's actually, I enjoy it. It's really fun. This will be a multi-week project where you guys basically try to apply some of the skills that you've learned from class, right? And then at the end, we have a design competition and there will be a winner. People got gift cards last year. And then for the very last class, we will do a trivia competition, or no, this will be the last class. The second to last class is the trivia Jeopardy type, trademark, right, competition, and everybody gets gift cards for that too. So that is the end of the lecture. Before we go take a bathroom break and then come back, does anybody have any questions on organizational or anything we talked about? I think I'm well ahead of schedule, which is good. So no questions. Everybody's good? We're happy? Okay, I'll see you guys back in 5-6 minutes. Thank you for watching Introduction to Basic Concepts in Engineering. Has this piqued your interest and you want to learn more? Much of the course content and the images in this course are from the text Introduction to Basic Concepts in Engineering for Adept High School Students by Andrew S. Heinz, PhD. While the textbook is not essential to successfully follow all class videos, It is an excellent resource designed specifically for introducing a student considering engineering to the field and for preparing them for the next steps. It contains many additional topics not presented due to time constraints, as well as additional practice problems and answers. The full text is also available on Amazon. Also, find us on Facebook at SHS Intro to Engineering.